Thank you so much, Sushanta, for this very kind introduction, as well as the invitation to be here and give this distinguished lecture series lecture. And when I look at the people who have spoken under this, it's quite humbling experience. So thank you very much. I came here almost 8-9 years back when this whole program was taking shape, and I see wonderful things happening in the last few years. So as mentioned, I'll be talking on this 2D crystals. But last night when I was having dinner with Sushanta, he also mentioned that there is a very strong interest in WIN in soft matter areas, which I also happen to work on for the last so many years in my career. So I dabble in both hard and soft matter, and my talk primarily will be on the hard condensed matter side. But I just thought I'll spend about 10 minutes to give you a flavor of the current interest is there in our group on soft matter systems, not giving details, but just give you a feel, which has some interesting issues being addressed. So we are interested actually in sheared soft matter systems and active matter. And both are, as you know, are the paradigm of non-equilibrium statistical physics. And one system where we have invested some reasonable effort is to understand colloidal glasses. There was a beautiful talk in the morning on the glasses. And for us, glasses are out of equilibrium system with complex landscape. And we would like to see if this landscape can be used to store memory of a disturbance. So structurally it will look the same, but can we have a way to store memory? So this is a very recent work. We succeeded in demonstrating that. So I just flash a slide on that just to let you know. And then I'll come to my talk proper as given in the abstract, but there also I will do slight variation looking at the interest in WIN. So the first experiment which is going on in my group for the last 3-4 years is to construct nano-heat engines. So we would like to know, can we extract work from bacterial activity, bacterial energy, and make a equivalent of Carnot engine or a Stirling cycle? Is it possible? With one colloidal particle, is it possible? So this so we all know, I'm not going to just remind you that heat energy converts heat or chemical energy into mechanical work. And really the heat engines were the triumph of classical thermodynamics. So what you have is a working gas, and you have a hot reservoir and a cold reservoir. So you have, for example, in a Stirling cycle, you have gas in a piston cylinder here. So first you do at a high temperature isothermal expansion. This is where you will get the useful work done. You can connect flywheel or whatever you have at your disposal. But at this time in a Stirling engine, which you have at the same volume, you cool it. It is called isochoric cooling because you don't get any work done. It's the same volume. But at this time, now you do isothermal compression, where you will work on the system. So you will not get work out of it, and then at the same volume you go to high temperature, cold to high. So this was demonstrated almost 260 years back, that if you do this, you will get a net work done. You can calculate the efficiency, and Carnot engine is slight variation of that. Instead of this, you have the adiabatic cooling. And this is something all very well known in classical thermodynamics, and we have lived with it, and civilization has gained immensely. So in the last 10 to 15 years, in statistical mechanics literature or in the community, in non-equilibrium StatMech, there is a question being asked that can we construct efficient and powerful artificial motors at micro and nano scale? Is it possible? And if that is possible, then one could have applications in transport cargo inside microchannels, cells, microfluidics, and so on. And how to do that? So one point I just want to say, which has been very critical, that when you reduce the size of the system and you work with very few particles, it is not just the mechanical shrinkage of the parts, but you have a very fundamental difference that all the quantities, thermodynamic quantities, are hugely fluctuating. So you really, the variance is same as the mean. So you have to work with fluctuating quantities and see, even with those fluctuating quantities, the concepts within classical thermodynamics can be carried over. Answer is yes, theoretically, and the whole field of stochastic thermodynamics has come up in the last 10 years to show it is possible. And the first demonstration of this experiment was done by Stuttgart group. So they literally translated piston cylinder into a optical tweezer. So optical tweezer can expand and contract with the laser light intensity, and you make only one colloidal particle in the trap. So one colloidal particle replaces your huge gas. And what you measure, like in other experiment, you measure the displacement of this colloidal particle as a function of time, which is of course having fluctuations. And what was shown was that if you do exactly like a Stirling cycle, when the colloidal particle is in a hot bath, you have lot of fluctuations, and now you decrease the laser light, you expand the trap, and then you keep on measuring the displacement of the particle, and now you cool water, for example, from 90 degree to 20 degrees, and now the particle will have less motion, and then you do exactly what you will do in a classical system. And the beauty was that by using this, they could show that you can get a definite work out of it, which agrees with the stochastic thermodynamics. So the question we asked 3 years back, can you really take this concept not to a thermal reservoir, but to a non-equilibrium reservoir, where temperature is not the relevant parameter, but activity or so-called noise of the system is a variable. So we said that we would like to have same temperature T hot and T cold, so-called same, but activity is very different. So what we did was, in recent experiments, we took those colloidal particles which will be trapped in a trap, but along with bacteria which can have activity varying very widely. So we vary the temperature by 20 degrees, and at the body temperature, bacteria are very activity. They impart energy to the colloidal particle, and when we cycle the temperature to, let's say, 20 degrees, the bacterial activity reduces, but they are still alive. And now we have shown, which is theoretically it was not obvious that it will be the case, even in this situation we get a useful work done and efficiency is very high. So I'll just flash the results without giving into detail. So we measure the colloidal particle displacement when bacteria is very active. So this is like now isothermal expansion will be replaced by isoactive expansion, same activity. Now we reduce the activity of the bacteria and do this cycle. And what we showed recently, that indeed if you get the cumulative work done versus the cycle of this heat engine, this is the passive point, which is not even visible on the scale, but this is this line. But as you have more and more activity of the bacteria, you choose different conditions of bacteria, and the effective temperature is very high because they are very active, and you can get 200 times more work done from this bacteria, and you can vary the bacteria at your wish. And we showed that the average work done per cycle, this is what matters, for the passive engine is 0.03 kVTC, but now it is almost 100 or 150 times more. So the bacterial activity has been converted now to a useful Stirling cycle. And we also showed now the efficiency earlier was 5% of the passive engine, but now with different activity we have reached 50%. So the biological motors are at close to 50 to 80% efficiency. So now we have shown where theoretical underpinning is still not fully worked out, but now it has given thought that how to really understand this. So this is something we did in our lab, which is still going on. Another activity in our group is to understand flow of soft material, which is again a very popular topic. Just to remind you, if you plot viscosity versus shear rate for a Newtonian fluid, it is independent of gamma dot. But if you have a viscoelastic soft matter, the viscosity can decrease at high gamma dot or it can increase, which is called shear thinning and shear thickening. And huge billion-dollar industries are based on shear thinning and shear thickening because all your cosmetics and so many other industries depend on that. And the cement industry is hugely affected by shear thickening. So what we showed, so this is something known in the literature, that if you take silica colloids and plot viscosity versus shear stress, for low volume fraction, it is not very interesting. But above 43%, you can see that viscosity will decrease first at high stress, but now it will increase. And this is the part which is called shear thickening. And this has enormous application in bulletproof vest, body armors, shock absorbers, and so on. So this is not only now in lab, it is now people are trying to translate it into applications. But the only point I want to bring out is that this is almost at 50% volume fraction of silica particles. So what we asked in the, this is one of the results, what we asked was, can you really decrease the volume fraction to very small one, so that the weight of the material is very small, but still you can get shear thickening. So what we did was, this is like when I was working on carbon nanotubes for devices, we had this idea that we take nanotubes in the solvent where they do not disperse. So they form fractals or fractal objects. So they are highly fractal. So even when the weight fraction is only 0.58%, not 50, they form this percolating fractal structure. And what we are now playing with the fractal friction. And what we showed, a few years back and now continuing with more experiments, this viscosity is extremely small, almost close to a few times water, but at high stress, it increases 5 orders of magnitude. So it just cannot move. And this is something happening. We understood some of it, that at this stage, what is happening is, these are the carbon nanotube fractal flocks, which are really jamming with each other. So this has enormous applications, and question is, can we extend to other fractal objects and so on. And more recent work is on colloidal rods instead of fractals, which is somewhat different from the spheres, and this is still an ongoing problem. So this is the last slide in soft matter, just to whet your appetite if some interest. So what we have done is, we form a two-dimensional colloidal glass of bubbles with soap bubbles, good old soap bubbles, but you have to practice for 6 months to get the stable soap bubbles which can stay for about 20 hours without popping off. If you get that correct, then we shear them with a plate and measure quantitatively their stress response. So they have a yield stress. It's like a colloidal glass. What we have shown is, in that colloidal glass, you can store memory. So the idea is, you disturb it with some amplitude, then you go home, come back, and then you see that exactly at that shear rate, the amplitude, something happens in the measurement, and you exactly know the system remembers it. So this is the remembrance of the mechanical structure, which looks exactly identical. You can't make out there is a difference, but because it is a complex landscape, it stores memory. It can store multiple memories, and editor probably was fascinated by this picture, so he put on the cover page of April issue of PRL, and a Physics Today article has just come out, that how experimentally you can use amorphous system for storing memory. Now, this is not that it will do any practical memories like electrical memories, but it's an interesting concept in complex landscape, and it brings in similarities to charge density waves and so on. So I think this is so much for my foray into soft matter, just to tell you what kind of questions we are asking. But now let me go to this talk on 2D materials, and all of us know that this graphene not only is a wonderful material, but it also inspired most of us to explore other 2D materials. So now 2D materials were always there, but the sensitivity to look as 2D materials was not there before graphene. So it's so now you have tons of layered materials, and the more emphasis now is also that if you have a non-layered material, can you make it still a 2D? And there are already interesting hints. I just took these slides that you have graphene family, you have chalcogenides, you have this topological insulators, and you have so many oxides, and these were actually in the bulk form, but now you can even make few layers or monolayer. So just let me paraphrase for those who are not probably in photonics for living, that these 2D materials have a huge opportunity, and it's just beginning to be explored, because we can cover a wide spectrum of electromagnetic spectrum, starting from HBN, from 6 eV band gap, to graphene, which is 0 band gap, in between MOS2 and black phosphorus. So huge opportunity, and now with heterostructures in place, you can really play what you want to do. So just to remind you the things which affect the photonic properties, of course you have a quantum confinement in a reduced dimension. So you have reduced electric screening, so you have large binding energy of excitons, and of course trions also you can get 2 electron and a hole bound. So all that is beautifully seen even at room temperature in MOS2 and few other 2D materials. So you have strong Coulomb interaction, which is the key point of this 2D material. You have strong interaction with light. You can see the absorption coefficients are large, and even monolayer of graphene absorbs 2.3%, and MOS2 layer almost 10% at excitonic resonance. And this is something which has given rise to whole field to couple them with waveguides and cavities, because they are naturally passivated without dangling bonds. And vertical heterostructures have come, and more importantly now twistronics, where you play with the angle between the two layers, and this discovery of superconductivity in bilayer of course has put a lot of emphasis on it, and the optical properties are still getting starting to be explored. Of course electronics is another feature, and so on. So in the next 35 minutes, what I want to do is a flavor of 3 stories from the lab, which will bring out the light matter interaction in these class of materials. So one is we use ultrafast spectroscopy to look at this light, the interaction of light with these materials. In particular, I'll take the graphene case. Second part, which we have been using to show that Raman spectroscopy is a very powerful probe beyond characterization. And you can look at the field effect transistor devices of these materials and really ask quantitative questions on those devices when you are doing in situ Raman scattering. And the last part is motivated again by WIN program. Lot of emphasis I heard yesterday on the sensors. So I just thought a very simple platform which we have shown, extremely cheap sensors, combining fiber optics, which is so very well developed, along with 2D materials. And this seems to be working for many situations we have tested. And these are extremely cheap sensors, and you can do multiplexing of these sensors. So let me see if I can give you a feel of what we are doing. So first part is to look at ultra-fast response of graphene. So if you photoexcite, what happens to the carriers? Because that will decide actually what will happen to your devices. And in that, the goal, which is of course true for all 2D material, that we would like to have new material discovered, new architecture for these applications, for example here, and all these applications need a very intimate knowledge of thermalization and cooling dynamics of carriers. For example, in solar cell, you know when you create photo-excited electron hole, how do they behave, when do they recombine, and in devices, what limits the mobility of the carriers. All that information is very critical and these ultra fast measurements give you one quantitative handle to address those questions. So for in particular graphene, as I said, this is a gapless band structure, flat absorption, but and also this unique electron-electron interaction, because the screening is very little because there is nothing below and above. So the electrostatic interaction is strong and it is not screened as much as in 3 dimensions. And our interest is to find out carrier relaxation pathways and quantitative numbers on the scattering cross section if we can. So that's the goal of the ultrafast community. And another feature which cannot escape us, that in graphene it's a Dirac electron. We all know that because the dispersion is linear at the K point, and this Dirac feature brings a very important thing, that there is a helicity conservation where the spin and the angular momentum are locked. So you avoid the backscattering, which gives you high mobility of the carriers. Even at room temperature you get high mobility of carriers in graphene. And more importantly, it has now opened up a whole avenue for the 3-dimensional analog of graphene, where the Dirac cone is in the bulk, not on the layer alone. And we have been looking at what they call Dirac and Weil semi-metal, which is a topological feature. So this is the idea now, to combine topology of the electronic wave function and see whether we can add some interesting properties. So already there are applications promised and demonstrated, some of them, and for example as a ultra fast optical modulator, terahertz modulator, photodetector, and so on. So all these applications need quantitative information on carrier relaxation pathways. So the experiment is very straightforward and simple. Simple quote unquote, because it takes a while to set it up, but the idea is pump probe experiment. Now you have a pump beam which can excite the sample, and what happens in the sample is a non-equilibrium state. You need to read out. So you send a probe pulse, which is a very weak pulse, at different delay times, and ask what is happening to the probe pulse, how much it is reflected or transmitted. So that information is quantified in these experiments. Now you have many possibilities. In our lab we have the pump lasers covering entire visible range using optical parametric amplifiers, and probe is anywhere in the visible. But today's talk is discuss the more recent work which we have been doing for last 5 years, terahertz probe. So we will be doing optical pump, but looking with terahertz pulses to look at what happened to photoexcited carriers. So terahertz is a beautiful range because it's a very low energy photon. You can see that 1 terahertz is only 4 milli-electron volt. So it's very close to the Dirac point in graphene, and it's a very small energy scale. And this is something which I thought would be interesting for you to see quantitative information being extracted. So in our group we have interest in all these kinds of graphene, more recently in twisted bilayer and also graphene. So you can now functionalize single layer graphene by the known amount of hydrogen. Some people are also doing fluorine, and it opens up a band gap which changes the optoelectronic properties quite remarkably. So we are interested in looking at graphene as well. So first experiment you do is you grow your samples by CVD mostly. These are all CVD samples because you need about 1 millimeter of the sample, because terahertz radiation wavelength itself is 300 micron. So you cannot do on a 5 micron exfoliated chip, which is what we used to do when we were making devices. Here CVD is the savior. So you can make single layer graphene with different dopings and measure the real part of conductivity as a function of terahertz frequency. And it is, you can see that it is high conductivity, low conductivity by varying the carrier concentration in a variety of ways. You can do for bilayer, you can do for graphene. Once we know these samples, of course this technique is very powerful and used in the industry now for doing the conductivity map of graphene. So this is quite a standard thing now in the last few years. The terahertz conductivity, which spatially resolved conductivity, is a good measure of graphene quality. So my interest is to look at terahertz photoconductivity. So we excite with optical laser light, 30-40 femtosecond pulse, and we would be asking what happens to the change in conductivity. So from now on, I'll be talking only on photoconductivity. So this is the experiment. You put a visible laser, all these carriers, they relax. This is what we want to probe. And at that time, you put a terahertz radiation as a probe and vary the probe time with respect to pulse and ask what happens to carriers as a function of time. And this is something we explore. And first thing is you measure terahertz conductivity as a function of delay time. And this is something, the first obvious thing to do. And what do you expect? What we expect is that pump photons will make electron hole pair, increase the conductivity of graphene, and conductivity will increase. This you measure that by the transmission route. You measure the transmission of the graphene and convert into conductivity. No brainer, and it just works, and the conductivity decays over 5 picosecond. So this is the relaxation time of carriers which we want to understand. So what is happening, let me give you the gist of this. What is happening is that in these analysis, first the photoexcited carriers which come at this point, they have a high electronic temperature. They achieve high electronic temperature in about 20-30 femtosecond, and then they cool down to lattice temperature by emitting optical phonons. But when they come very close to the Dirac point, that is not possible. So they start participating with acoustic phonon. And with acoustic phonon plus disorder can explain this 5 picosecond relaxation time. So this has all the information which one can take out. But the surprise was in those times that when you measure different types of graphene, you get different results. So this was the case in the literature that for our high doping graphene, the conductivity decreases on optical pumping, which is counterintuitive. But on low doped graphene, it behaves what you expect in a semiconductor, like conductivity will increase. So this time, the negative and positive, we wanted to understand quantitatively. So how do we understand this? So for that, so we did various types of graphene, I told you, and the similar analysis, similar conclusion is valid, that for low doped graphene, conductivity increases on pumping, but for high doped graphene, it decreases. So then at the same time, another group did these experiments using electrolytic gating and showed on the same sample by varying the doping, you can go from negative to positive photoconductivity. Now, this is something I just will give you a quick understanding of that because it's quite informative, that what we are having is with terahertz, we are looking at this interband processes and the terahertz is getting absorbed by those carriers. Now, this will always give you conductivity which is positive on pumping. And this we can show from a Drude form, you can show that it will be mostly positive with some negative part from some subtle reasons I will not go into, and this will not explain what we observe. This cannot explain. But at the same time, there was a theoretical development which came to our understanding that in this beautiful paper, what they showed was a mechanism which happens in the following way. It's called multiple hot carrier generation. So you get this photoexcited electron, and this electron interacts with the existing electrons which are already there in graphene. And because of the strong Coulomb interaction, it makes them hot. So this electron interacts with them and also makes them hot. So that is why it is called photoexcitation cascade and multiple hot carrier generation. So you get many hot carriers just with one photocarrier. And this is something can be quantified and shown that this mechanism indeed leads to conductivity which decreases on photoexcitation. because the lifetime of the carriers has changed because of this mechanism due to strong Coulomb interaction. So now you put both of them together, intraband and this electron, hot carrier electron, and we showed you have a master plot now. If you give me a graphene with the known Fermi energy, both the mechanism put together can explain where you will get negative photoconductivity and where you will get positive photoconductivity. So that was one thing we started with, but then we went on, and this is the part which is quite intriguing. We now want to measure photoconductivity spectrum. We want to measure how does photoconductivity vary as a function of frequency at different delay times and at different temperatures. Now again, what is our expectation? Drude law, because we grew up with Drude law. So we will say, well, the photoconductivity will simply be a Drude law, and you will have a momentum relaxation time entering here. This is the Drude weight, which of course you have to do carefully for graphene because these are Dirac electrons, and that's all. But if that is the case, immediately you will see that the real and imaginary part of the photoconductivity, which we measure in the experiments, will have the same sign. There is no way to make real and imaginary part different sign. But at the same time, when tau is very small, this is negligible and this will be frequency independent. So you will get a very boring graph of conductivity change as a function of frequency, which is like flat, and both are of the same sign. But what we saw, and this was the first experiments, that when we measure this, the conductivity of the single layer graphene was very interesting. The real part was negative and the imaginary part was positive. And this was completely different from Drude, what you expected. So as usual, there is a crisis in the lab because you don't know how to explain. So you do what physicists do best, you put a Lorentzian, and Lorentzian will explain everything in life, because if graph in Drude doesn't work, put Lorentzian. And we did that because other groups had also done, and lo and behold, it beautifully explains. But there is no understanding why there is a resonance frequency, which is a crossover here. Why this term? Where is it coming from? Lorentz, where is the oscillator strength coming? So till now, there is no clarity on what is the origin of this Lorentzian, but it fits. We gave various possibilities and all these were ruled out because it does not vary with laser power. All that we ruled out for graphene. And then we were stuck when we changed our graphene samples, many of them, and when we went to low doped graphene, this is the data which is very different from high doped graphene. Imaginary part is positive, real part is positive with high, with this kind of a shape, and nothing works. We put Drude, we put Lorentzian, nothing works. So even this ad hoc assumption is not sufficient. So then, and this is where we decided that this is not good for us to do. Let's go back to textbooks and ask what is the origin of conductivity. And what we did recently, which is what I'll show you, we did this for bilayer and single layer. I'll just give you the summary of this. This is the data on a bilayer, very non-trivial photoconductivity, and this is the fit, quantitative fit from a model, which I'll just try to explain in about 4 or 5 minutes. And this is something which is working for single layer. We have shown it now for carbon nanotubes. We have shown it for graphene. So this is something which we think is a way forward. So what we remind, I hope you don't get pushed or repelled by after lunch talk with equations, that the conductivity is very well known in textbooks. It's a Boltzmann transport equation. You have the density of state of the material, you have the momentum relaxation time, which depends on energy, electron temperature and lattice temperature, you have the derivative of the Fermi function and Fermi velocity. Everything is well, if you can put these numbers, can you really do? But the $1 million question is, which nobody had tried, everyone takes tau energy independent, you pull it out and you get the simple Drude form. So we were paying for our inefficiency or laziness to do the full understanding and take a simple assumption that momentum relaxation time is energy independent. But this is not the case. And various processes now you have to consider for this. And if you understand microscopically that, then you can get the total effective rate, put this, do the energy integration, calculate the conductivity at different electronic temperatures and see if it can explain your experiments. So this is the project which took us 2 years, where we considered various contributions like scattering of electrons from ripples, dislocations, add atom and structural defects, long range Coulomb interaction from charged impurities, carrier scattering from acoustic phonon, carrier scattering from surface optical phonons. All this we did, and I will not give you the details because they are all in the paper. We know the density of state of bilayer. We put for each process the microscopic equation, quantum mechanical expression, and the only thing unknown for us is this interaction potential and their density, the two things which we take as experimental adjustable parameter with a caveat. We do all this energy dependence, which is quantitative. This is not a scale arbitrary. It really has to see if this is correct. We put all these mechanisms, and lo and behold, at the end of the day, you do those integration, do the evaluation at different electronic temperature, different temperature, lattice temperature, and the experimental data fits extremely well. If you fix these impurity concentration and the oscillators, the V naught for one temperature, and nothing has to be varied after that, and everything gets explained. And the same thing happens when you vary the delay time. So here also, so experiment data has to be consistent with this calculation only with one set of disorder density. And at the end of the day, we realize that we can have quantitative numbers on these parameters, and it also tells us that in bilayer graphene, the maximum contribution is coming from short range scattering of the carriers from this defects disorder, which is mostly the ripples and so on. So this was satisfying, and it works for single layer and it works for graphene and so on. So I think I will not give you the single layer results because that is again the similar line. But to summarize, that now we have a quantitative understanding of photoconductivity, which gives you the idea what mechanism is contributing to scattering of photoexcited carriers, and gives you an estimate of how much disorder is there. And this quantitative understanding hopefully will tell us how to optimize the material, because now we can really see the connection between growth conditions and terahertz photoconductivity and how we can relate. So this is the summary of the first part, which I have put it as a take home message, that this ultrafast spectroscopy gives you a quantitative understanding of carrier dynamics, leading to tuning of the material and how to optimize them for optoelectronics, energy and other applications, because most of the applications in photonics need these parameters and these mechanisms. So second part of the story, since I come from Bangalore, which was the hometown of Professor C.V. Raman, and the Raman Institute is about 2 kilometers from the institute I work in. And I don't know how many of you seen this picture of Raman with this calcite crystal. And Raman spectroscopy is almost like a, extremely common thing. I am sure in WIN you will have about 10 of them, because every sample you can characterize very, very fast with Raman spectroscopy. Now, it so happens that in the nano field, Raman has made a big dent because the Raman signatures are very unique of all these nanomaterials, be it one layer, be it 2 layer, be it graphite, be it carbon nanotube. All these materials fortunately have different Raman fingerprints, and you can study them. Now, this is something we all do, that when we prepare this nanomaterial, we characterize them using Raman scattering. But question to be asked is, can you do beyond that? Can you look at the physics of these materials using Raman spectroscopy as a readout? So in particular, can you look at electron-phonon coupling, something which we also do in ultrafast, but now in Raman spectroscopy? And can you look at electron-electron interaction physics? Can you look at hot carriers? And can you look at coupling between sublayers in heterostructures when you make this 2D heterostructures? So this is where the Raman scattering is playing a very significant role to give us this information. So I'll give you just two examples of this from our work, and literature has other examples. So first step is that when you make a material, 2D material, you would like to make a device, and the simplest device is the field effect transistor, which is what you do. It's like a hydrogen atom of the devices. You immediately make a field effect transistor, source, drain, you have a gate, let's say 300 nanometer SiO2, and then you have a back gate. And this is from the very early work, 2005, that conductivity change as a function of back gate voltage. This is the Dirac point, and this is what gives you the conductivity. And it is symmetric on electron and hole side, something shown almost 13 years back. Now, what we did at that time, this is 2008, when we were really not making our devices. So the devices came from Andre Geim and Novoselov and through Cambridge, that we made these devices, and instead of back gate, we put the top gate electrochemically. So we have an electrolyte and a platinum wire which acts like a gate. So the bilayer, which is only 1 nanometer, replaces 300 nanometer of SiO2. So whatever you can get with 100 volts, now you can get with half a volt. And you can get very large doping of the devices, electron or hole, and you can really show that it's a beautiful electrochemical transistor. Now what we do, we put this device in the Raman microscope and look at the Raman signatures as a function of gate voltage. And that is very interesting. So we measure these two Raman features. It's called a G mode and a 2D mode. Don't worry about the details. Some of you must be using it. And this has a huge dependence on the gate voltage. This is the top gate. And the beauty is that when I plot these numbers, let me show in the next one. This is the top gate voltage. Now you see that my voltage is only 0 to 3 volt or minus 3 volt. 100 volt has gone because we are doing electrochemical gating. And the G mode shifts by almost 30 wave number, and which means we are varying the Fermi energy on this side. This is the electron doping, this is the hole doping, and the line widths are also quite different, which is very unusual. I will not go into detail. And the 2D mode is very different from G mode. So by combining these two, you can get now quantitatively the doping level and whether it is electron or hole doping. And this has become a metrology tool. And I was surprised on the last count, this paper has gathered about 4,000 citations or something, because now it's a quantitative number you can get out of your devices just by a very trivial Raman experiment. So, so now what we did at that time, we did this theoretical understanding of why such a thing is happening, why the line width is decreasing on doping and not increasing, which is what usually happens. What happens to frequency, which is increasing and not decreasing on doping. This is a non-trivial effect. I will not go into detail. And graphene is a beautiful system where the electrons and hole dynamics are coupled. They are not like separated like other semiconductors. So it is like a non-adiabatic effect. You put all that in the theory, and what you get is a quantitative estimate of electron-phonon coupling parameter. And this is something very interesting, that Raman scattering can give you such detailed information. So we did this for black phosphorus single layer more recently, and I don't want you to go to the numbers, but here what happens is that this electron doping effects are much more than the hole doping, and the B2G phonons are not affected, only the A1G phonons are affected. So the symmetry of the phonon is important, and we can find out which phonons are coupled. For example, in MOS2, you have two phonons here. And what we have shown at that time, that if you make a similar device, only the A1G phonon is affected, this frequency, and nothing happens to E2G phonon, because these phonons have different way of vibrating. A1G phonon has atoms moving out, and E2G phonons are in plane. Now this again you can go to theory and compare with experiment. This is what we did, and you can again get a quantitative number on this interaction. Now this interaction is symmetry dependent. This is the message of this. And what we did more recently, this is a tough sample to make devices. Single layer we could not succeed till today. So we have made this 2HMOT2 devices by exfoliation, and we have done the same experiment, and we have a big surprise. So what we are showing now is that in these devices, I will not go into detail, let me show you the final result. A1G is very little affected, 0 to 0.4 wave number. Line width is not much changed as a function of carrier concentration. But the E2G phonon, which was not affected in MOS2, is exactly opposite. It is softens a lot and much more than A1G. So it is, people would have thought MOS2 and MOTE2 are same. There will not be any difference in the symmetry properties, but actually it is different. And the reason now is, which is what we are deciphering, it is related, again not going into detail, what is the symmetry of the wave function at the conduction band. And the fact that conduction band minimum is at different points in these two materials really is at the back, that A1G phonon is affected in MOS2 and E2G phonon is affected in MOTE2. So all this exercise tells us that Raman spectroscopy is not only for characterization, but it's a very powerful probe to measure symmetry controlled electron phonon coupling, which is again an important parameter to understand. The last 5 minutes? 5 minutes, I'll just, so last part is just to, this is my, this is not the main theme of my group, but this is what I have done with a collaboration, because it was an idea based experiment and it worked out. So what we have shown is, you take the fiber Bragg gratings and use them as sensors for biological sensors or chemical sensors. So what is the idea here? So the idea is that when you take a fiber and you write a grating with a UV light, so you know the pitch of the grating, and when you put light here, only one wavelength depending on this Bragg condition will be reflected and others will be transmitted. So experimentally what you can measure is this Bragg wavelength, which is lambda b. So essentially you just measure, very simple one, and this is at the heart of smart materials which people put in buildings. You put this fiber Bragg grating, and if the building has some issues, then this lambda b will shift because the grating spacing will change, which is lambda. So what we are doing now, instead of that, we said let us change N effective, the refractive index of the fiber. Now this is not very easy if you have a clad. So what we did is simple innovation. We removed the clad in a controlled manner and put the right chemistry to deposit different types of nanomaterials. We tried nanotubes, we tried graphene, now MOS2, you can even use quantum dots. You have to find the right chemistry. If you do that, then what you can now do, you have a material which is very sensitive to change in refractive index when something happens. So on this nanomaterial, you put the right antibodies, and then when the right antigen has to be detected, you will have this coupling and change in the effective refractive index, which will shift lambda b. So experimentally, we are measuring change in the Bragg condition as a function of concentration of that what you want to detect. So question is, does it work? So we were surprised that it is very sensitive and very specific. So what the few years back, 2015, now more experiments have been done. We wanted to see a glucose sensor, which is like a guinea pig. Everyone wants to do that as a first time for the sensor. But here what we did to bring specificity, we put this aminophenyl boric acid. This is the one which is sensitive only to glucose. And what we show, so we coat this material with reduced graphene oxide, on which you have chemistry to put 4-APBA, and now this is ready to detect glucose. So these are the experiments done with my colleague Professor Asokan, who is an expert on the fiber Bragg grating, and the joint student Sridevi and my student Vasu worked on this problem. So what we did, we also made FETs and did the same experiment. It works, where we see the change in conductivity of graphene or nanotubes. But more interesting was when we measure this Bragg shift. And we are plotting the shift of the Bragg wavelength in picometer versus concentration of glucose in molar. And what you see is that our limit of detection is 1 nanomolar. This is the limit of our detection, and it is fairly linear to a very large range. And this is something we compared with the available sensor, and it's extraordinarily cheap to make this. These are throwaway sensors. And then we went on to see, can it detect glycolated hemoglobin, which is an expensive test, I guess. In India it is expensive, I don't know here. So the question is, can we make a cheap glycolated hemoglobin test? And what we did, I will again not go into detail. Again, it detects beautifully after lysing the blood samples. It is extremely sensitive to this glycolated hemoglobin. And here this is a summary that our limit of our method is 8.6 × 10⁻⁵ millimolar, which seems to be better than the available literature. And this is something again we feel has a huge potential. So other thing we did was CRP, C-reactive protein, and there also it seems to be extremely sensitive, and in presence of all these interfering proteins, it still works. So we have huge amount in our paper, you can see, of urea, glucose, creatinine. In spite of all that, you can detect unequivocally the signatures of CRP. Seems to be working. And again, this is not to spend time, but it's one of the best right now in the literature. The recent one, which is what we did, is again heavy metal sensing. So can we take this concept to heavy metal sensing? So this is done in collaboration with, of course, Professor Asokan, but a person who is really the very, very smart organic chemist. So what he has shown in context of some other studies, if you take this molecule, which is what I shown here, this can really attach to mercury. And the limits which I have said should be here. This is what we want to detect from 184 nanomolar to 736, because that's a bad limit. And what we have shown now, we did this very recent experiments, and now we can show that it is extremely linear right up to 1 micromolar. And these are the average over about 13 samples. And in the presence of interfering salts like sodium chloride, copper sulfate, whatever is possible in water, we put that and it can still detect. So again showing a very high sensitivity of this method and specificity. So just to sum up, we think it's a platform technology using fiber Bragg grating and nanomaterials, and it's very cheap, highly sensitive and specific. And now we have shown that you can put multiple sensors on the same fiber with different pitch. So in one shot, you can get all the specificity of supposing you want myoglobin or along with CRP, all that you can do in one sensor and detect at the same time. So I think with this, just to summarize slide, I showed you on the role of ultrafast spectroscopy in understanding the carrier dynamics of these materials, how Raman spectroscopy is a powerful measure of all these interactions. It could be electron phonon, it could be other interactions. And the last part was to touch marrying the fiber optics, which is highly developed, along with 2D material to replace as a clad material and use it as a platform. So these are the people who have done all the work. Sorry, what did I do? So this terahertz part, Srabni, now she is in Cambridge as a postdoc. Bilayer samples were from SKKU, from Young Healy group. Topological Institute, which I did not talk, I apologize. This is done with Mithun, and all this sensor work is done in Professor Ashokan and their group, and funding from DST. Thank you very much for your patience. Thank you once again for inviting me.
For the Raman pieces, what happens about this interface of the SiO2 versus your real material? Is the Raman the effect? Because when the samples are above the interface,
good question. Yeah, so it's a very good question. So this is related to the puddles, charge puddles. So at the charge puddles are very, very much influencing the dynamics near the Dirac point. So near the Dirac point, you have that physics which affects actually our ultra-fast experiment, which I did not tell you. So when your graphene is close to the Dirac point, we saw that no theory works for us. So what we think is at that time, the charge puddles are playing a major role, and this has not been fully understood. So near the Dirac point, you have to worry about it. Unless you do a suspended graphene, but they have their own problem. Or HBN is what people are trying, and we have also tried. HBN reduces the puddle, but not fully. So it's a very important point in graphene. Yeah.
Any questions?
Yeah.
I like your soft matter material, the stuff on that. How are you able to store information in a system that is already chaotic? You have to take a snapshot of everything?
No, that's the beauty. Okay. So what we do is, if you look image-wise, it does not look different. So what we do, we take this amorphous system of the bubbles, we shear it, let's say 10 times at a given shear strength, some amplitude. Then we go out and come back. Then we keep on measuring the amplitude of that what we disturb and measure some quantity, in our case mean square displacement of each bubble, and find that exactly at the time, at the gamma which we use to train, the system becomes extremely quiet. Mean square displacement just falls to zero. Not zero, but very low value. And moment we go away, it again goes up. So it's a very unique signature, and now we have shown you can store 2 or 3 memories, 2 right now. So 2 memories can be stored, again you can read out. So you should see that paper.
Is this a very niche area of research, or are there, because this sounds like an area that I've never heard of before, that people would dote on, or people would be skeptical of?
No, there is okay, so I will answer this. A few years back, there was a computer simulation showing a possibility of this memory storage. But multiple memories were stored by putting some noise and so on. So that simulation showed, what we are showing is actually the landscape when you have a dense system does all the things. So it is related, I will not go into detail, we can talk later. It is related to fluctuating to absorbing transition. So there is a non-equilibrium phase transition which is really behind this. So what happens in soft matter, when you shear it, particles hit each other for 5 cycles and then they learn how to live with it. So when they learn how to live with it, that's the where place you store memory. So now people are asking, so if you read Physics Today article on our article, actually she has brought much more connection than what we have said. And so it has a lot of open questions now, and nobody had shown that experimentally.
That's pretty cool. I'm going to talk after.
Yeah.
Thanks for a nice talk. For the fiber optic, the Bragg ratings work. So how thick are the coatings of the RGO that you use? Are these like single layers? Sort of?
Yeah, okay. It's a good question. What we saw that our RGO is mostly single layer, but there are multiple, but that did not affect the performance. If it is,
in the coating, like is it a coating of like a
yeah, so the coating is good if they are monodisperse as much as possible. So we centrifuge and all that we do, and then it is beautiful coating. But you have to functionalize your fiber. Without that, they will not stick. So we did that, and if you want to put MOS2, there is another trick. So, so recently we have been trying gold nanoparticles. So there is another chemistry for that. But the beauty is now all those nanosystems you can use along with the Bragg grating readout. So Bragg grating is essentially measuring the change in refractive index, and that change is delta n by n is 10 to the power minus 5. It is comparable or even better than SPR, surface plasmon resonance, and it's extremely cheap. It's not a expensive thing. If you have a reader, it's extremely cheap.
Okay, let's thanks Ajay.